Okay, hi guys. So in this lecture, we'll be comparing the basically we'll be continuing on seeing the reactivity selectivity um, principle. Okay, so let's actually start off with that. So suppose let me draw the energy profile when we actually react RH with Br. Okay, RH with Br dot. So if R is a tertiary carbon atom, directly the carbon atom which is directly attached to the hydrogen atom is a tertiary, then we have this energy graph, and if it's secondary then we will have something like this, and if it's primary then we will have this. But let's see the RDS for comparing RH with Cl dot. Okay, so what actually happens here is it is at this energy level, okay, RH, and if we have this would be the 1 degree, this would be 2 degree, and this would be 3 degree. The 3 degree is the 3 degree, 1 degree, 2 degree is the degree of the carbon which is directly attached to the hydrogen atom. Okay, so let's write some notes here that RDS of bromination is endothermic and RDS of chlorination is exothermic. Okay, so RDS of bromination is endothermic and RDS of chlorination is exothermic. Okay, and Br2 is more selective and less reactive. Okay, Br2 is more selective in the sense that it will only choose to attack on 3 degree carbocation or 3 degree carbon atom, which in intermediate will form 3 degree carbon free radical. Okay, so Br2 is more selective and less reactive. Okay, and similarly Br2 is the reason is Br2 is more selective because there is a significant difference in activation energy in the formation of free radical. Okay, so let me write it down as it as well. So Br2 is more selective because significant difference in activation energy in formation of a free radical. As you can see in the graph that 3 degree, 2 degree, 1 degree graph, the energies are activation energies are pretty high. Okay, next that obviously, and it's less reactive. I forgot to mention that, and less reactive because it's a endothermic step. Endothermic step. Okay, and similarly you can say that Cl2 is more reactive and less selective because it's a exothermic step. Okay, only there is a minute difference in delta H of 1 degree and 3 degree. Rest, even the 1 degree will undergo halogenation. Okay, because the delta H is negative. So Cl2 is more reactive and less selective. Okay, so as a matter of fact, let me write it down as well, that rate of abstraction of, or rather reaction of Br dot, rate of reaction of Br dot with 3 degree, 2 degree, 1 degree is 1600 is to 82 is to 1, and similarly rate of reaction of Cl dot with 3 degrees to 2 degrees to 1 degree alkane or carbon atom directly attached with the hydrogen atom is 3.5 is to 3.8 is to 1. Very minimal difference. Okay, hence Cl is more reactive, less selective, whereas Br is more selective, less reactive. Okay, let's see some examples here. We have CH3 here and CH3 here. We pass it in Cl2 in presence of H nu. So we'll get two products, Cl at this carbon atom and Cl at 1 degree carbon atom, CH2Cl. Okay, so both products we get, but obviously major product would be this, but there won't be substantial difference in the percentage yield of this and this. Okay, because it is more reactive, less selective. Okay, so we define a term called RF, which is a rate factor. Okay, which is nothing but the number of 3 degree hydrogen atom into rate of 3 degree hydrogen atom. Okay, so we have rate is predefined, which is 5. Okay, and RF factor for this is for 3 degree. RF factor for 1 degree would be number of 1 degree hydrogen atoms okay into rate of 1 degree hydrogen atom. Okay, so how many total number of so in this case total number of hydrogen atoms were 1. Okay, and rate of 3 degree hydrogen free radical is defined as 5. Okay, now in this case number of 1 degree hydrogen in this case is 3 plus 3 plus 3 9, and rate, let's say, of substituting a 1 degree hydrogen atom and substituting with Cl is, let's say, rate is 1. Okay, this is some hypothetical number which we are defining, or rather from the experimental fact you can also cross verify that for Cl the rate of reaction with 3 degree hydrogen atom is 5 and 1 degree hydrogen atom is 1. Okay, so rate with 3 degree hydrogen atom is 5 here and rate of 1 degree hydrogen atom is 1 here. Okay, so RF factor is 9 here. Okay, so what is the percentage yield in this reaction? You can calculate by dividing yield as the RF factor for that one particular 1 degree carbon hydrogen atom or 3 degree hydrogen atom divided by 5 plus 9 total. So yield for, if we calculate what is the yield for 1 degree substitution, it would be 9 divided by 14. Okay, and yield for 3 degree is 5 divided by 14. Okay, let's see another example wherein we have something like this compound. Okay, and we are reacting it with Cl2 and H nu. We get this product plus obviously we'll be getting this product. So let's see which would be in which would be the major product based on the rate factor. So rate factor for 2 degree would be, how many number of 2 degree hydrogen atoms are there? Only 2. And what is the rate? We discussed 3.8 here. Okay, so 2 multiplied by 3 by 3.8, and whereas rate factor for 1 degree hydrogen atom would be, how many total number of 1 degree hydrogen atoms are there? 6. 3 plus 3, and then what is the rate for 1 degree, which is 1. Okay, so in this case it would be 7.6 and this would be 6. So you can calculate the percentage yield of each product. Okay, now let's see some more example. So suppose we have this alkene, okay, and when you pass it in H2 in presence of PDBaSO4, we get this structure cis. Okay, this is also called Lindlard's catalyst. Okay, and if we pass it in sodium or ally's presence in presence of liquid NH3, this is also called Birch reduction. We have discussed all these reactions in previous lectures, so we will be getting a trans alkene. Okay, so what happens in I'm just this is just an example to summarize or to remember how the two products are formed. So in case of H2PDBaSO4, the mechanism is simple. On a plate or on a surface of PD, we have hydrogen molecules which directly goes and attack the alkene over here. Okay, and two hydrogen atoms are added from the syn addition take place, or from the same side two hydrogen attacks. Okay, whereas in Lindlard's catalyst, the complete mechanism is there, wherein you get the nitrogen atom actually releases electron, and that electron goes on to attack the alkyne group, and on the alkyne group, due to the steric hindrance reasons, it forms a trans product. So we'll be discussing the mechanism again if you guys are finding it hard to remember. So the mechanism is as follows. So the mechanism is, first, in the first step, sodium will dissociate into Na plus electron. In the second step, what will happen is this electron will be attacking the alkyne. Okay, so on the attach while it is attacking it, two products can be formed. One is definitely will have CS3, one electron here. Okay, one of the electrons will be transferred to this carbon atom. Okay, so we'll be getting C minus. Okay, or two electrons here. I'm also showing a negative charge here. One can be this product. Okay, and another can be this product. So which is more stable? Obviously this is more stable. Why? Because of the steric hindrance reasons in these two bulky CS3 groups. Okay, so this would be formed and not this. Okay, and from this, what will actually happen again is, it will take let me redraw it. It will take H plus from the NH3. This actually lone pair will actually attack on the NH3 to convert itself into something like this. H and NH CS3 would be here, plus NH2 minus would be there. Okay, formed, and then one more electron would be released from the Na, and as a result, this electron will again be will get associated with this carbon atom, and will again get a negative charge here, C and CS3 here. Again in NH3, it will attack on H plus, and as a result we will get a trans alkene. Okay, so this was the example of BITS reduction. Okay, so in the next lecture we'll be seeing some more examples on the same, and some more examples on identifying the major products based on the reactions or mechanism which we discussed in the previous set of or previous lectures. Okay, so till then, good luck and goodbye.